Hello, we are Team Electra. Today we are going to talk about fundamental geometric algorithms. These are our team members' contribution. I am Prince Cyril Deva. I'll be the first one presenting today, starting with knot insertion and knot insertion algorithm. The next team member Ravi Kiran will talk about surface knots and geometric modeling lab, followed by Sai Pawan with knot refinement, Bezier decomposition and design examples. Finally, Lindsay Fields will talk about knot removal and degree elevation/reduction. Knot insertion. Let's C to the power of WU be a NURBS curve defined on U0 to be a non-decreasing sequence of real numbers where U sub I are called knots and U is called a knot vector. This gives us the equation C raised to the power W U summation I is equal to 0 to n sub I comma p of U pi W, where P defines the control points of the curve. Now if we insert U bar into U, we get a new knot vector U dash, where U dash is also a non-decreasing sequence of real numbers. If U sub U and V sub U dash denote the vector spaces of the curves defined on U and U bar respectively, then clearly C to the raised to the power of WU has a representation on U bar of the form C raised to the power WU summation I 0 to n plus 1 n bar IP of U Q sub I raised to the power of W, where n bar IP of U are the pth degree basis function on U bar. These are some of the applications of the knot insertion: adding control points to achieve increased flexibility in shape control, subdividing curves and surfaces, evaluating points and derivatives on curves and surfaces. Generally, the process of determining Q sub I raised to the power of W in the above equation is called knot insertion. By setting and solving the system of linear equations, we get this equation that we can see here. By using previously defined properties, property 2.2 to be exact, and implying, we get summation I is equal to k minus p to k n sub I comma p of U p sub I to the power of W is equal to summation I is equal to k minus 1 to k plus 1 n bar sub IP U Q sub I raised to the power of W for all U sub k U sub k plus 1 for these ranges of I. Now finally combining the above two equations with linear independence of basis functions, we arrive at P sub I W is equal to Q sub I raised to the power of W, and P sub I raised to the power of W is equal to Q sub I plus 1 raised to the power of W for the ranges of I. If we if we express n bar for a range of I, we can arrive at the equations shown here. Now we write n bar sub I for n bar sub ip of u. We get these equations. Due to the time constraints, we have to skip some of the steps. Anyway, finally we arrive at this equation that you can see here. And next slide. Now, by equating coefficients and using the naught vector u in place of u bar, we obtain, by equating it to 0, we arrive at the equation that you can see here. And now for all ranges of I, we set alpha sub I is equal to u bar minus u sub I whole divided by u sub ip minus u sub I, 1 minus alpha sub I u sub I plus p minus u bar by u sub I plus p minus u sub I. Now, by using the linear independence of the basis function, we can conclude that q sub I raised to the power of w must be equal to alpha sub I p sub I w plus 1 minus alpha sub I p sub I minus 1 w for k minus 1 plus p is less than equal to I is less than equal to k, which allows us to get the final equations by computing all the new control points. Q sub I w, that is q sub I w is equal to alpha sub I p sub I w plus 1 minus alpha I p sub I minus 1 raised to the power of w. Here we can see the example for knot insertion. If we set p is equal to 3 and knot vector u and the control points p0 to p7, then when we insert u bar is equal to 5 by 2, then we can compute the new control points. On the right hand side, you can actually see how the calculation takes place. As we can see, the results are in fractions from the previous control points. The graph that you can see on the right represents the new basis function before and after the knot insertion. And if you see to the right side, to the left side, sorry, control polygon, you can see the control polygon after inserting the u bar. Inserting a knot multiple times. Sometimes we need to insert a knot multiple times. Suppose u bar belongs to u sub k plus 1 has a multiplicity s, and it is inserted r times, where r plus s is less than equal to p. Then we denote the ith new control point in the rth insertion step by q sub I comma r raised to the power of w. This equation that you can see here represents inserting a knot r times into the NURBS curve, which you can see right here. Here we see an example of inserting a knot multiple times. Here, if we set the multiplicity s is equal to 0 and r is equal to p times, Then we can generate a triangular set of control points. The outer control points and the inner control points are discarded. The final control points are obtained by transversing the resulting table in a clockwise fashion, starting at the top of the first column generated. Let r is equal to 3, the curve is defined on 0, 0, 0, 2, 3, 3, 3, 3. Now we end up with the following cubic. This is obtained by inserting naught 3 times into the original curve. We can see the previous control points and the new control, and here are the new control points after they have been inserted. Here is the algorithm for knot insertion. This is much simpler than the math discussed in the previous slides. This algorithm computes new curve corresponding to u bar r times, where up and uq are knot vectors before and after the knot insertion. Well, this slide shows the applications of knot insertion. The application shown here is splitting a cubic curve. If we start with the original curve C that you can see here, and then we split it at u is equal to 1 by 2, resulting in the points C1 and C2, which are then split at 1 by 8 and 3 by 8, resulting in the following points C11, C12, C21 and C22. And from the next slide, my team member Avikiran is going to take over.
Knot insertion is done on surface or curves to gain control or change parameters of the shape, while also making sure the overall shape doesn't change. The shape can be shape of curve or other surface. So the process of knot insertion is based on insertion method done on B-spline curves. And the control points of the knot surface are Pwi, J, where I exists between 0 to n and j exists between 0 to m. The formula and equations of the B-spline curves are also applicable on the surfaces. The only difference being it is applied on rows and or columns of the surface. Shown here in the figure below is a cubic quadratic surface, and the control net changes to Qi, j when knot insertions are done, and I changes to like 0 to n plus 1, and or j changes to 0 to m plus 1, whether depending upon whether the direction is u or v, the knot insertion directions. If the direction knot insertion done in both directions, then q at wi, j will become 0, where I is between 0 to n plus 1 and j is between 0 to m plus 1. Now let's talk about knot insertion in a single direction. Shown here is a scenario of when the knot insertion is done in u direction. The control net changes from p, the max of the control net changes from p3, 0 and 3, 3 to q4, 0 and 4, 3. But otherwise, the control net is very similar to that one without any overall change. Now let's talk about knot insertion under direction. Here it's v direction. The number of control points and their positioning changes. If we can see here, it's P0, 3 and P3, 3. It changes to Q0, 4 and Q3, 4 when the knot insertion done in V direction here. Now if we see knot insertion in both directions. So as we can see here, the Initially it was P3, 0, P0, 3 and P3, 3. When not in session, then in both the directions, it changes to Q0, 4, 0, Q4, 4 and Q0, 4 with the control net being much smoother than the initial draft of control net. And we can also see there are many more control points, meaning we can move each control point to the desired position without affecting the whole of the fabric of this control net. Shown here is algorithm for surface knot insertion. So this is very similar to the knot insertion done on curves, the algorithm, but the difference is that we there are two loops, one for u direction, one for v direction, depending upon whether we're doing it in single direction or two directions. And also while calculating alphas, we don't need to include it within the loop. We just need to input it at the almost very end because alpha doesn't depend upon number of control points. As I was saying previously, this whole thing will be again repeated for the v direction till here. So now let's talk about splitting a surface in single direction. Now if multiple insertions are done in u and or v direction in the surface, then the surface splits into two or four subsurfaces. Shown here is a control net for a surface when it is split in u direction because of multiple insertions in u directions. As we can see here, it splits into two parts, and that we can see even on the surface. So if the knot insertions are done in v direction multiple times, then it also splits into two subsurfaces. We can see this is the control net and this is the surface, but it's in the another direction. This is along the v direction here. Now if this surface is split in both directions, this happens when the insertions are done in both u and v direction multiple times. We can see the control net divides into four sub control nets, and this is same in the surface also. Extraction of isoparametric curve. Now to extract a curve CWU dash, we must do U direction insertions P times on each of the m+1 columns of control points. So the total number of knot insertions will be P into m+1. Similarly, for extracting a curve CWV dash, we must insert a total of Qn+1 knot insertions, with n+1 being the rows of control points and Q being the number of knot insertions in V direction. So shown here is an example of isoparametric curve extraction U direction. This is the curve. Now let's talk about surface extraction. The subsurfaces formed from multiple knot insertions will have a common control point in form of SU, V. The order of insertions is dependent upon number of P and Q, where P and Q are the number of knot insertions in U and V directions respectively. So if the number of P insertions P is greater, then it will be the SU, V will be calculated using P into Q+1 U direction knot insertions and Q V direction knot insertions. If Q is greater than P, then it is Q into P+1 V direction knot insertions and P U direction knot insertions. The partial derivatives and normal vectors are obtained using corner point derivative formula. And these derivatives and normal vectors are for the subsurfaces.
Good afternoon. My name is Paul, and here we are going to discuss about knot refinement. So there is no difference between knot refinement and knot insertion. If we try to insert a single knot, that is called knot insertion. If we try to insert for multiple times into the curve, that is called knot refinement. It is often necessary to insert many knots at once, and this is called knot refinement. So, as you can see, knot refinement can be accomplished by multiple applications of knot insertion. So, we can implement knot refinement by implementing knot insertion multiple times. But we need to distinguish between these two problems here because we have more efficient algorithms for knot refinement. Let's see those. So here are the applications of knot refinement. So the decomposition of B-spline curve and surface into the constituent of polynomial pieces is one of the applications which we are going to discuss in the future slides. Edging of two or more knots in order to obtain a set of curves which are defined on one common vector. This is an important construct in certain types of surfaces. Obtaining polygonal approximations to the curves. Refining knot vectors brings the control polygon closer to the curve, and in the limit, the polygon converges to the curve. Let C W U. Let this equation be defined on the knot vector. Let this curve be defined on the knot vector. U is equal to U0 to UM. Then let X is equal to X0 to XR satisfy Xi is less than or equal to Xi plus 1, and this which also satisfies U0 is less than Xi is less than UM for all I. So here this is simply a curve which is defined on the knot vector U, and we are taking another knot vector X which satisfies these both conditions, that is Xi is less than or equal to Xi plus 1 and U0 is less than Xi plus 1 for all I. So the problem is we have to insert the elements of X into U and the corresponding new set of control points, that is QIW for I is equal to 0 to n plus r plus 1 is to be computed. The solution steps doesn't require any mathematical calculations. Those are very simple. At first we have to find two indices A and B such that UA is less than or equal to Xi is less than UB for all n. It follows that the control points P0W to P-1W and PB-1W to PNW do not change. Therefore, copy of these appropriate QIW locations. Copy this to the appropriate QIW locations, leaving room for R plus P plus B minus A minus 1 new control points. Denote the new knot vector by U bar. The U bar is basically U matched with X. Copy the nodes on either end which do not change, and then we have to go into the loop and compute the new control points, match the elements from U and X into U bar. The loop can work forward, that is starting at Q A minus P plus 1 A, or backward starting at Q B plus R minus 1 W. So this is the curve. So the cubic curve, this is the cubic curve built for knot refinement, and figure B represents the first midpoint knot refinement, and figure C represents the second midpoint knot refinement. This is the example for curve knot refinement curve. So this is the algorithm which performs knot refinement of curve. This algorithm is proposed by Boehm and Prats. It works backwards and overrides intermediate control points while inserting a knot. Surface knot refinement. Here we are going to discuss about surface knot refinement. Let SW of U comma V is equal to sigma I is equal to 0 to n, sigma j is equal to 0 to m, n I comma p of U, and j comma q of V, p I comma j superscript W be a NURB surface on U and V. A U knot vector refinement is accomplished by simply applying previous algorithm to the n plus 1 columns of the control point. A V refinement requires n plus 1 applications of surface knot insertion algorithm. The algorithm can be organized so that the redundant operations are eliminated. So basically, to perform surface knot refinement, the U knot vector refinement. So we have to implement the previous algorithm, that is not refinement and curve algorithm, m+1 times on the u0 vector, and we have to implement the surface knot insertion algorithm and v on v0 vector. So this algorithm can be organized so that the redundant operations are eliminated. Here is the algorithm which performs the knot refinement on the surface. Here we can see the example for surface knot refinement. The figure A represents the third midpoint refinement in the u direction. Figure B represents the second midpoint refinement in the v direction. Figure C represents the refinement in the u direction and the second in the v direction. An important application of knot refinement is the problem of decomposing a Nub's curve into its constituent polymer segments, as we have said in the application section. In such a conversation, the first step is to decompose the curve into its piecewise Bezier form. So the first step of this conservation is to decompose the curve into its piecewise Bezier form. The Bezier control points of the segments are obtained. This can be done by the Bezier control points of the segments are obtained by inserting each into a knot until it has multiplicity p. This is done in two ways. Pass through u and build the refinement vector x, and then we have to use the knot refinement algorithm, which is defined before. Nub's curve decomposition into piecewise. Here we are going to discuss about Nub's curve decomposition into piecewise Bezier. So the algorithm decomposes a Nub's curve and returns NP Bezier segments. The QWJK is the kth control point of the jth segment. The local array alphas contains the alphas with the indices shifted to start at 0. This is the algorithm. The input will be in this variables, and the output will be in this. So here is the example for not decomposing a curve into its piecewise Bezier. The curve and its so figure A represents the curve and its control polygon before the decomposition, and figure C represents the curve and its control polygon after the decomposition. Figure B represents the basis functions defined over these values, and a figure D represents the basis functions after inserting knots 1, 2, and 3 two times each. So now we are going to discuss about on how to decompose Nub surface into piecewise Bezier. This algorithm shows the organization of surface decomposition. The routine composes a Bezier strip, i.e. a Nub surface that is Bezier in one direction and B-spline in other direction. The routine must be called twice, once in the U direction to get the Bezier strips, and the strips must be fed into the routine in the V direction to get the Bezier patches. So this is the algorithm. The input will be in these values and the output will be in these variables. So here is an example for this is an example for decomposition on surface. This is a control net of the surface before decomposition. This is the control nets of the surface after decomposition. And figure V represents the surface defined over U and V vectors over these values. And figure T represents the various surface patches.
We will now discuss knot removal, which is the reverse process of knot insertion. As such, we again start with a NURBS curve defined on U, and without removing the end knots, we let U sub r be an interior knot with multiplicity s in U. The new knot vector we form when we remove U sub r t times is U sub t. Similarly to how we added 1 to the upper bound of the summation every time we inserted a knot, whenever we remove a knot, we subtract 1. Therefore, U sub r is t times removable if the NURBS curve has a precise representation on U that sums from 0 to n minus t, where n bar is again the pth degree basis function on U sub t. More simply, this means that U sub r is t times removable if the two curves given here, are geometrically and parametrically representing the same curve. Just like with insertion, knot removal generally refers to the process of determining the new control points Q. An effective knot removal algorithm must also be able to determine if a knot is removable and how many times it can be removed. Knot removal is useful for converting from power basis form to B-spline form, as the process is to convert the segments to Bezier form and piece the resulting Bezier segments together to form a B-spline curve. Then, using knot vectors in which all of the interior knots have multiplicity equal to the degree, remove as many knots as the continuity of the curve or surface allows. Other uses of knot insertion, and therefore their eventual removal, include increasing the number of control points in order to interactively shape a B-spline curve, and linking B-spline curves together to form composite curves. We will now provide an example of knot removal. As usual, the algorithm operates on the 4 coordinates of the control point. Consider the cubic curve given here. We assume that the original curve is defined by this arc from point 0 to point 6, and U here, where the superscripts denote the step number in the knot removal process. So let's consider removing U equals 1, or U sub 6, in the middle here. The first derivative is continuous if and only if p over the distance between knots U sub 6 and U sub 3 times the distance between point 3 and point 2 at step 0 equals p over the distance between knots U sub 7 and U sub 4 times the distance between point 4 and point 3, also at step 0. By setting U sub 4 and U sub 6 equal to U, since they're what we're removing, and rearranging the terms, we get point 3 at step 0 equals the distance between U and knot U sub 3 over the distance between knots U sub 7 and U sub 3 times point 4 at step 0 plus the distance between knot U sub 7 and U over the distance between knot U sub 7 and U sub 3 times point 2 at step 0. Finally, letting point 2 at step 0 equal point 2 at step 1 and point 4 at step 0 equal point 3 at step 1, and simplifying this fraction to alpha 3 yields point 3 at step 0 equals alpha 3 times point 3 at step 1 plus 1 minus alpha 3 times point 2 at step 1. In this case, the equation is just the formula for inserting U equals 1 into the knot vector with 1 as a double knot, since U sub 7 is U sub 6. Likewise, the second derivative at U equals 1 is continuous if and only if U equals 1 can be removed a second time, and the third derivative is continuous if it can be removed a third time. In general, to solve one of the systems of equations shown previously, we start with the first and last equations and work inward, computing the new control points. If the number of equations is even, such was the case for the second derivative, then the final new control point is computed twice. A knot can be removed if the two control point values are within a meaningful tolerance of the old control point on the left-hand side of the equation. Conversely, if the number of equations is odd, then the control points are all computed only once, and the last two are substituted into the middle equation. If the resultant substitution is within a meaningful tolerance of the old control point of the middle equation, then the knot can be removed. To compute new control points for a single removal of U, with multiplicity s between 1 and p, we use the general equations point I at step 1 equals point I at step 0 minus 1 minus alpha I times point 1 minus 1 at step 1 all over alpha I, and point j at step 1 equals point j at step 0 minus alpha j times point j plus 1 at step 1 all over 1 minus alpha j. If you want to compute new controls for removing U multiple times, you can use the formulas point 1 at step t equals point I at step t minus 1 minus alpha I times point I minus 1 at step t all over alpha I, and point j at step t equals point j at step t minus 1 minus alpha j times point j plus 1 at step t all over 1 minus alpha j. Clearly, this latter form is just a generalization of the case with t equals 1. We can generalize these equations into simple algorithms for removing U either once, or k times. However, it is generally unknown in advance whether a knot is removable, and if so, how many times. This algorithm instead attempts to remove a knot up to 6 times, up to s times, where s is the multiplicity, and returns the actual number of times the knot was removed, along with the new knot vector and control points. We will finish knot removal by discussing 2 additional knot removal algorithms. The first is to remove as many knots as possible from a given curve. The first image here shows a curve with single, double, and triple knots. In the next image, the single knot here is removed. You can see how the path now has to deviate outward from the 2 surrounding knots to accommodate the removal. This is more apparent in the last image, where we removed 3 of the triple knots up here. The last knot removal algorithm we will discuss is surface knot removal, where we attempt to remove as many knots as possible from a given surface. As before, the first image is the original surface. We then remove the triple knots here in the U direction to create a new surface with this more folded pattern. The next image removes just one knot in the V direction, forcing this other V knot to shift downward. Finally, we show how the surface is altered if knots are removed in both directions. We will now move on to degree elevation. Assume you have an nth degree polynomial curve, as shown here. By setting a sub n plus 1 equal to 0, you can obtain a similar curve of n plus 1 degree, which is actually the same curve embedded in a higher dimensional space. Assuming we instead had a pth degree NURBS curve on the knot vector u, we should be similarly able to elevate the degree since the curve is piecewise. That is to say, there must exist some control points q and a knot vector u hat, such that the two curves here are equivalent. Geometrically and parametrically, and are just embedded in different dimensional spaces. The term degree elevation generally refers to the process or algorithm by which one computes these control points and knot vector. As usual, degree elevation algorithms are applied in 4-dimensional space. The NURBS curve we're using has 3 unknowns, n hat, u hat, and q. To determine n hat and u hat, we can assume u has the following form, where the values of m denote the multiplicities in the interior knots. Because C is a polynomial curve on each non-degenerate knot span, its degree can be elevated on each such knot span. The curve is C to the p minus m continuous at a knot of multiplicity m. Since the degree elevated curve must have the same continuity, it follows that the same knot must have multiplicity m plus 1 for a higher dimensional curve. Therefore, we are able to determine n hat and u hat using our assumptions for a lower dimension. The only thing we have left to do then is to compute q. The most straightforward, but also highly inefficient method to solve the system of linear equations formed by evaluating the different dimensional curves is equivalent. We will instead discuss a simpler algorithm to solve for q, which involves 3 steps. First, extract the Bezier segment from the curve using the Bezier extraction methods discussed above. Next, select the ith segment to degree elevate. Finally, remove the unnecessary knots between the ith segment and the subsequent segment. These steps are shown in the following images. The first image, here, is the original cubic curve which we will elevate to the 4th degree. The first step is to obtain the first Bezier segment by inserting a knot here. We then elevate this first Bezier degree. Now we will compute the second Bezier segment by again inserting a knot here. We then elevate this second Bezier segment up top. At this point, we can remove the two unnecessary knots between the first two Bezier curves, so these two knots would be removed. We finally degree elevate this last Bezier segment and remove the unnecessary knots between the last two curves to yield a fourth degree continuous curve. This example shows a sample curve degree elevation. Starting from a third degree curve here, we are able to subsequently raise the degree to 4, 5, and 7. And as the degree increases, the control polygon converges to the curve. Degree elevation is accomplished for surfaces by applying the elevation techniques to the rows and columns of the control points. We can see this in the following example, where the original surface net is elevated by 1 in both directions, then by 2. The last topic we are going to discuss is degree reduction. Let C of u be a pth degree B-spline curve on the knot vector u. We say that C of u is degree reducible if it has a precise representation where C and C hat are equivalent on the knot vector u hat. Even though it is always possible to degree elevate a curve, not every curve is degree reducible. However, degree reduction has great utility for reversing the process of degree elevation. Following a similar strategy to the one we set up for degree elevation, the algorithm for degree reduction has 3 steps. First, extract the ith Bezier segment from the B-spline curve. Then, reduce this segment as opposed to elevating it. And finally, remove any unnecessary knots between the ith segment and its previous segment. These steps are shown in the following images. The first image, here, is a 4th degree B-spline curve which we will reduce to 3rd degree. The first step is to extract a Bezier segment by inserting a knot here. The segment is then degree reduced. Extract the second Bezier segment over here. This second segment up top is also reduced, and we remove 2 knots between the first 2 segments. The last Bezier segment is degree reduced, and 2 knots are removed between the last 2 segments to produce the final 3rd degree B-spline curve. We will now finish up with Bezier degree reduction. If we are given a pth degree Bezier curve, and we denote its degree reduced counterpart by C hat, we can compute the unknown p by rearranging the formula for Bezier degree elevation. We must consider 2 cases, when the degree is even and when it is odd. Assuming even degree, we obtain the following formulas for the value of p. An example of this can be seen in the image here, which reduces the degree of a Bezier curve from 6 to 5. Now let's assume the degree is odd, like in this image, reducing a Bezier curve from 7 to 6. This differs from the even case only in that, for the purpose of symmetry, the middle point, which we denote as P sub r, is computed as the average of the 2 components on either side. I will now hand off the presentation for further examples.
So let's talk about some knot insertion examples. Shown here on the left side and left figure here is a B-spline curve with 10 control points, and the knot insertion is being done. The red dots on the left figure are the knots being inserted. And on the right side, we can see that the extra control points, the control points which seem unnecessary, are removed. But we can also see that the curve is not disturbed in this whole knot insertion in this. This is also like the knot refinement. Yes, and let's see another example. In the top left, we can see a design, and it has some n number of control points. And on the top right, we can see the same figure is slightly more smoothened out and curved. This happened when a single subdivision took place. And when subdivision happens, the n number of control points is almost nearly doubled, because when subdivision happens, there between any two control points on the curve, another control point is added. That is what a subdivision is, which is basically not insertion. And here we can see in the bottom, the curve, the curve is almost smoothened out. This is because of multiple knot insertions. We could gain much more control over which direction the curve should be turned, and at the same time make sure uh, the remaining part of the curve is not disturbed. So by this we can say that knot insertion allows better control over the curve and gives us much more uh, precise and these are our references. Thank you. Uh, here is a I'm drawing a Bezier curve. Then going into the edit mode and drawing a random curve. Now you can see here like 1, 2, 3, 4, 5, 6, 7, 8, 9 control points on this. Now if I try to interact with these control points, I can see we can move it here and here and here. Let me put the thickness so one can see clearly what's happening. Yeah. So now I take this control point, move it here, and then this control point and move it slightly. So I can change the shape of the curve using the control points. Now let me do knot insertion. Here we first I highlight this and then use subdivide. I only divide this curve into ones, which means I'm just basically adding one control point between any previous two control points. And this is the result: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Almost, there's basically a double almost. Now, as you can see here, now uh, get a control point and move it. Now see, this only this part of the curve moves. Well, last time when I tried to move a control point, it was like the much bigger area, much bigger part of the curve. So adding control points or not inserting knots in the curve helps us in controlling the curve better, and also making sure the shape of the curve doesn't distort much. Yeah. So yeah, this is can be a example, said to be example of knot insertion, knot refinement, and this can be even done on not just a curve but also a surface, and it also responds in a similar way. Yeah. So thank you.